All right. Hi, everybody. Thanks for tuning in today, and I hope you're having a great Friday. This week, our seminar speaker is Dr. Margaret Landis, who's currently a researcher at the University of Colorado at Boulder. Dr. Landis is a planetary scientist whose research focuses on studying impact craters and impact processes, and also water ice processes and water ice deposits on planetary bodies in our solar system, including Mars, Ceres, Earth's moon. I know she's also thought about other asteroids as well. And she approaches this work by combining modeling, so thermal and vapor diffusion modeling, also with spacecraft data sets like images, digital elevation models, thermal infrared spectroscopy, gamma ray spectroscopy, neutron spectroscopy, just to name a few. Dr. Landis earned bachelor's degrees in physics and astronomy at Northern Arizona University. Actually, I met her when she was an undergrad a long time ago. And she completed a PhD at the University of Arizona. She then did a postdoc with the Planetary Science Institute working on the Dawn mission. And so I'm sure that some of the work that she's going to be sharing today is from that time. And then, as I mentioned, then she sort of transitioned into a postdoc at UC Boulder, and then now into her current researcher position. And so thanks again, Dr. Landis, for taking the time to talk with us. The floor is yours. Thanks again.
Thanks so much. Let me make sure I can change my slides here. Yeah, thanks so much, Francis, for the great introduction. Again, like Francis mentioned, we met at my second LPSC ever when I was an undergraduate. So yeah, your colleagues will be your colleagues forever, kids, in a very good way. Okay, so I think Francis hit on all the high points I wanted to mention here in this background slide. And I think the key takeaway is that even though the Dawn mission is over, we're still thinking a lot about Ceres. And there's just a wealth of planetary data now of this largest asteroid. But there was a time where we didn't have that much data on Ceres. And one thing that's really interesting about Ceres is it's challenging a lot of preconceived notions about our preconceived notions about the solar system. So this is a toy solar system. The sun is on the left. This is not to scale because there's Jupiter. But this is kind of a notional idea to kind of walk through some of the history of ideas around how we've thought about Ceres, how we thought about asteroids, and what that means for our understanding of water and carbon in the solar system. So we put Jupiter in there. So we've got most of the mass of the solar system on here now. Well, we did with the sun, and now we have most of it. But we've known a couple of planets since either antiquity or the early 19th century or the early 18th or mid 18th century. So Mercury, Venus, Earth, and Mars, and then Saturn and Uranus. Uranus was notably one of the first kind of discovered planets known outside of antiquity. So it's really interesting that we get this period like 200 years ago where all of a sudden we're discovering more planets and trying to understand what that means for our solar system. So in a lot of ways parallels now. But this was kind of what we knew about our solar system in 1800, which of course things have changed a lot. One of the biggest things that changed was it was very fashionable in the turn of the 19th century to have astronomers make star catalogs. You'll kind of see this track through American astronomy too in the 1800s. But Giuseppe Piazzi was specifically hired at the Palermo Observatory as an astronomer to make a star catalog. And again, in a lot of parallels to now, Palermo Observatory wanted to put its map on astronomy, and they did it by buying this, at the time on the right, very nice, huge telescope and hiring an astronomer to run it. And so he was cataloging stars and then did the classic, oh, this star is moving way too fast compared to the background field. It must be much closer. What could this be? And so due to various mishaps that again are kind of paralleling our current time, Giuseppe Piazzi basically published a letter to APJ or AJ or Astronomical Journal, Astrophysical Journal equivalent of the time, with a couple of observations of Ceres, and then immediately got pretty ill and didn't respond to his mail. So I guess not responding to email has been another tried and true astronomer tradition for a long time. But there was this really big interest in where he had identified Ceres, because he said it was between Mars and Jupiter, which due to various numerical relations that don't actually have a physical basis in reality, unfortunately, but were present at the time, this is where a planet was predicted to be. So if Giuseppe Piazzi was right, that means they found another planet closer to the Earth than Jupiter, and this would have been a huge discovery. So Carl Friedrich Gauss did the calculation for where to look for Ceres next, and turns out Ceres was there. So next time you think about Gauss's law, it's also electricity and magnetism, but it's also discovering planets. So Gauss was a busy guy. Repeat observation was successful, and now that there have been multiple observations of Ceres verified by multiple additional people, you know it's a real object, and you can tell where it is in the solar system. So this was the confirmation that Ceres is somewhere between Mars and Jupiter. And so this is really interesting because all of a sudden there's a new planet. It has huge implications for understanding where the mass is, where other objects are in the solar system. And unfortunately, people kept finding more planets in this part of the solar system. So Pallas was discovered next, Vesta later on. Asteroids have numbers that the lower numbers correspond to early discoveries. A lot of asteroid folks will use the 1 Ceres designation or the 4 Vesta designation, though their reclassification in the 21st century is dwarf planets. Fewer people have used that classification, but if you see that, that's what it's for. Another one of my favorite asteroids is 24 Themis, which means it was the 24th discovered. And so all of a sudden you have all these objects between Mars and Jupiter, in addition to Ceres. Ceres is still the largest one, but all of a sudden you're starting to think, okay, so what's happening here? This is not one concentrated mass. This isn't what we were expecting. And then William Herschel decides to say, you know, Piazzi found such a small planet compared to mine. Does that really mean that what Piazzi found is a planet? Which again, parallels to things that we have lived through in our redefinition of things in the solar system. So William Herschel discovered Uranus in 1781. This was the first discovery of a planet that was not known since antiquity because it required a telescope to find. And of course, William Herschel did a lot, but Caroline, his sister, was part of their research team. And she went on to have, after the discovery of Uranus, a really successful career in comets. And she was one of the first women inducted in the Royal Astronomical Society in the UK. So like I mentioned, with the addition of Ceres, Pallas, Vesta, you start having too many planets. And for the next time you talk to somebody who's upset about Jupiter being demoted, you can say that you've met someone virtually who's still upset about Ceres being demoted, but this is a different issue. So there's a really great paper by William Herschel saying, here are my requirements for what's a planet. One of his requirements was an atmosphere, which again leaves poor Mercury out, but it seems like Mercury often gets the short end of the stick in these discussions. But again, what I'm trying to point out here is that the discovery of Ceres really upended our understanding of the structure of the solar system, what a planet meant. And then, okay, so if we want to understand the history of the solar system, what do these smaller objects between Mars and Jupiter really mean? Neptune again was discovered later on in the 1840s. So you're having this combination of larger, cooler gas giants being discovered in the outer part of the solar system and more rocky things being discovered closer to the sun. And when I started editing this talk, it was October 11th, and the NASA Exoplanet Archive said that in addition to the planets in our solar system, whether or not you count Ceres and Pluto, is over 5,000. So we've had, at least in the 21st century, in the late 20th, early 21st century, this huge explosion in understanding what solar systems can look like, what planets can look like. And so again, we're asking these same questions. What makes a planet? What makes a planet different than other small bodies? And what kind of chemical and physical processes are fundamental to solar systems? In a lot of ways, these are questions that are very closely linked to astrobiology. Are there other habitable environments elsewhere in our solar system or in other solar systems? But it also comes down to understanding fundamental physics and chemistry of how solar systems work. One of those fundamental physics and chemistry is that at least it had been an idea for quite some time. And a spoiler is that Ceres challenges this idea, which I'll talk about later in the talk. But for a long time, there's been this idea, which is thermally correct, where if you are closer to a star, things are hotter. If you're further away, they are cooler. And this just deals with the fact that the incoming radiation dies off as 1 over distance squared. So if you doubled the distance, you quarter the amount of radiation. And so in our solar system, oh, and Pluto's appeared good on my slides. In our solar system, out past Jupiter, things tend to be much colder and icier. Closer to the sun, they tend to be a lot hotter. And like I mentioned earlier, Mercury is both very small and very hot. And so the Messenger mission orbit, which was an orbiter around Mercury, was very well designed to make sure that their thermal constraints were met. So for the engineers in the room, if you really want a thermal management challenge, Mercury is a great one. Venus is another great one. But there's this idea then that closer things are hotter, further out things are cooler. That's kind of borne out in the chemistry we currently observe. The nitrogen ice glaciers on Pluto would not be stable in the inner solar system at all. And so understanding where this transition is from rocky to icy things is really important. And we used to think that the snow line fell somewhere in the asteroid belt. So there's different snow lines for different volatiles. In this case, we're talking about closer into the sun, water is a liquid or a gas. Further out, it behaves like a solid or a rock in some cases and has a lot more material strength. And it used to be thought that the snow line probably fell somewhere in the asteroid belt because Vesta was closer to the Earth than Ceres. Vesta didn't have a lot of signs telescopically of water ice at the surface, whereas Ceres, basically, as long as we've been observing it with modern astronomical instrumentation, the density is low. There are spectral signs on the surface of water. And so there was this hypothesis kind of pre-dawn that maybe Ceres is on the outside of the snow line, Vesta is just inside the snow line. And so if you go to explore both of these asteroids, you'll kind of capture this idea of where the snow line would have hit in the asteroid belt. And there should be one with a whole bunch of question marks on it. Sorry, I'm going to move the Zoom screen. Okay, and this is the one with a bunch of question marks because this is, like I mentioned earlier, a lot of discussion has kind of occurred around whether or not this idea is valid or not, because we know based on Grant and other dynamical models that small bodies were probably scattered multiple times throughout the history of the solar system. So is this kind of conceptual model of thinking about volatiles in the solar system accurate? How can we refine it based on measurements from Ceres? And what does this mean for carbon and water in the inner solar system? Because we clearly have it. We are walking, talking bags of carbon and water. So somehow carbon and water got back into the inner solar system. So questions I'm going to talk about in kind of today's seminar talk are water and carbon on Ceres' surface. How did it get there? What's its long-term stability? And what does this mean for small bodies in general? So small bodies are anything that are not fully in hydrostatic equilibrium, or that William Herschel would say, well, I discovered a bigger planet, so like that's not a planet, excuse you. And so this is applicable because even though Ceres is now the largest asteroid in the asteroid belt, there are other rocky and icy objects that we think either exist or once existed in the asteroid belt, one of them being the Themis family parent body. It was broken up probably a couple billion years ago in a large impact, but in the original parent body probably wasn't nearly the size of Ceres. But we see similar carbon and water on Themis family members today of asteroids. And so how do processes on Ceres suggest processes that might be happening on other rocky and icy bodies? What does this tell us about the chemistry of the solar system? Okay, so pre-dawn, this was our best image of Ceres. We can see some albedo variations, which are very neat. Like I mentioned earlier, we know that it has a low mean density, and modeling before the dawn's arrival suggested between 17 and 27% water ice by mass, which is a lot of water. And then another thing that I've done a lot of work on is that there was a suggestion that from telescopic observations that Ceres had an exosphere. So this is an atmosphere that is not gravitationally bound to the body, and basically where one mean free path of the gas is just as likely to send you out into space as it is to send you out into the surface or another molecule. And what's been really interesting, and the Kuipers et al. In 2016 detected them with the Herschel Space Telescope, which was a really precision measurement, but unfortunately, even then, these measurements were right at the detection limit of the telescopes at the time. So what would happen is, and this had been happening since the 80s, is that researchers would find a very marginal detection of an exosphere around Ceres that was water vapor. And then when they'd follow it up, they wouldn't find anything. So the state of knowledge back before the arrival of Ceres, or arrival of dawn at Ceres, was that we knew Ceres had a lot of water. We knew it was probably outgassing some amount of water vapor, but it was nowhere near cometary levels, and it was a really difficult observation to reproduce. And so it was kind of agnostic as to whether or not this exosphere was due to kind of currently active processes that were common or uncommon, or if this was just a detection issue where if you put some sort of observation in situ, you'd be able to see the exosphere more reliably. So there was a lot of mystery still surrounding Ceres back in 2015 when dawn arrived. So Dawn arrived in March of 2015. This was when I was in grad school. This was really exciting because one of my favorite things in planetary science is to get new images down and go, what the heck is that? And oh boy, Ceres had a lot of those moments. And so the instruments aboard Dawn are the framing camera. So this was both panchromatic and a color wheel. So depending upon which images you see, you might see different color filters there. There was a visible and infrared spectrometer. What was special about this spectrometer is that it went from, it spanned a really nice wavelength range. So we were able to get both some of the shorter wavelength features that are more characteristic of asteroid spectra that were collected from the Earth, as well as 3 micron and kind of out to 4-ish micron phyllosilicate stuff. I'm not going to go into too much of the mineralogy and the spectroscopy, but I'll do a little bit. And so the idea is that this would capture a whole range of carbon and hydrated mineralogy so we could really understand what was on the surface of Ceres. And then peeling back the layers a little bit on Ceres, the gamma ray and neutron detector was another instrument. What's really cool about neutron spectroscopy is it's not electromagnetic spectrum spectroscopy. You're actually relying on neutrons produced in the surface due to a variety of factors. And when you have fewer neutron counts, it means that the neutrons are actually hitting something in the subsurface. Neutron spectroscopy is good to about 1 meter, and it's particularly sensitive to hydrogen and chlorine and other things that are really good neutron moderators. So it's particularly sensitive to hydrogen, but you can also get other elemental abundances out of it. You can't tell what the structure of the mineral that iron, for example, is in, but you can tell the total weight % iron that's likely in a sample from neutron spectroscopy. And we also got gravity from spacecraft tracking. I'm not going to talk a lot about the gravity measurements, but I think that's one thing to remember with spacecraft data is as long as you went into orbit or the orbit was somewhat perturbed by the planetary body you flew by, you can get gravity data. Okay, so I showed you the image of Ceres before dawn. This is the Ceres after dawn, the mission, not the time of day. And so what's really notable about this is we can see, of course, all these craters on the surface, which were kind of expected. Things that were not expected are all these bright areas, which I'm going to talk about potentially ad nauseum here, because they're pretty unusual. Ceres albedo is about 9%. And so having much brighter areas doesn't mean that they're, snowfields, clean snowfields on the Earth bright, but it means there's a significant difference and a significant compositional difference. There's also all sorts of fractures you can see across the surface. Degraded craters as well as fresh craters. And I'm going to see if I can stop this movie at the right time to catch Occator Crater, which I'm going to talk about a lot today. There we go. It's turning into the field of view. Let's see if I can pause it. Okay, there we go. So this is Occator Crater. It's a 90-kilometer diameter crater. And these two bright areas, I'm going to talk about extensively in a little bit. So kind of to orient you, this is in the Northern Hemisphere, but it's not far north. So this is our view, and now you can see some of these really nice like pit chains. So there's a lot going on Ceres. And so this was our view afterwards. And so there are a couple of data sets that basically corroborate this idea that Ceres is a very water ice rich world. So this is the gamma ray and neutron detector water equivalent hydrogen map. So what you can do is you can say, okay, hydrogen is a great neutron moderator. So what does that mean for inferred amount of water? So how could you get these neutron results by adding hydrogen into the subsurface? And these are the results. So between 16 and 29 weight % water, the equator is desiccated and there is more water equivalent hydrogen at the poles, which to somebody who does thermal measurements is a dead giveaway for something is happening with the temperatures on this planet. Poles, so Ceres' obliquity is relatively low, so the poles are going to be receiving less solar flux than the equator. That's going to affect the temperatures. So this was one of the first initial clues of like, yeah, there's something happening that is latitude dependent, and the total incoming amount of solar flux is going to be latitude dependent. There's something interesting happening here. Other things that were really neat on the surface are these kind of low rate flow landslide deposits. You can get low rate flow landslide deposits in a lot of ways, but one of them is to have water ice kind of mobilizing the grains. And so from this work, it was hypothesized that maybe there's a lot of subsurface water ice, which confirms and kind of corroborates the neutron results. And then this is something I'm going to talk about, not in extensive detail, because this could be a whole seminar by itself. But here on the right is a Huna Mons. It is a large dome feature. It's probably constructional, and it's probably from some sort of water upwelling process. The challenge is that, I mean, this is also a small area to hit with impact craters, so this has been challenging to age date, but at least compared to its surroundings, it looks a lot younger. There aren't a whole lot of impact craters, and you kind of have these signs of mass wasting on the side that's re-exposing bright material. As far as we know, this depression is not related to a Huna Mons itself, so it's not like directly taking material out of the subsurface and piling it on the top. It's probably some sort of loading, unloading, buoyancy issue in the subsurface. It's been argued that instead of being a water ice dome or a water ice salt dome, this could be mostly salt doming, kind of like Upheaval Dome in Utah. The jury, I think, is still out on some of these things, but one thing that's really unusual about this is some of the biggest, highest relief on Ceres. So there's kind of one big mountain, some smaller hills, but this is kind of not something we would have expected, because this kind of relatively recent appearing dome indicates maybe there's still something happening in the subsurface. There's been spectral detections of water ice on the surface. Sorry, the sun is changing a little bit here. 9 water patches have been detected, and then potentially haze at Occator Crater. This is a really controversial measurement, and I have to always put the panel numbers in because I don't see the haze, but apparently there's a haze over Occator Crater in panel A that disappears in the late afternoon by panel B. This has been heavily contested within the Dawn team and within the community. So there's probably active processes happening on Ceres. My take is that they're not happening here for reasons I'm going to explain a little bit later. Okay, so post-Dawn, one of the things that we really focused on was the exosphere. And one of those reasons is that we want to understand how stable water ice is on Ceres and whether or not the water ice we observe today is representative of the amount of water ice that was in the past. Because if Ceres is constantly blowing off 6 kilograms per second of water vapor, that ends up being about 50 meters of total like subsidence over the entire asteroid over a long period of time. So that would be unusual and interesting. So some post-Dawn exosphere hypotheses include sublimation from the water ice table that's indicated by the neutron data, from postulated exposed surface ice. So like I showed previously, we know surface ice is appearing in 9 locations. That also means that landslides and impact craters are the kind of processes that are happening all the time. And so trying to understand how much additional water vapor you get for potential exposed water ice is important. Another competing hypothesis was solar energetic particle event sputtering. So if you do have water ice on the surface, it might be possible to knock water ice molecules off really efficiently with a solar energetic particle event. Whether or not we actually observed one hit Ceres to cause the exosphere is something that Villarreal and co-authors argue. But again, this could be a whole nother seminar topic. There's a lot to do with Ceres that's really interesting. And then finally, an optically thin polar water ice deposit where water ice has been deposited at the poles, and then something happens to destabilize it and it's released all at once. So what I'm going to dig into a little bit more is the amount of water vapor we can expect from exposed water ice content. So 9 locations were confirmed with spectral data to contain water ice at the surface. So what I did back as part of this paper was argue that you could get a substantial amount of water vapor from these 9 exposures, and if this is a constant process, potentially a lot more. So what I did is I calculated the slope and the direction a lot of these water ice exposures were facing, and you can do this using the digital terrain models that are available of Ceres and a thermal model that I had used previously to model the amount of water vapor coming from the buried water ice table. So the buried water ice table, kind of no matter how you slice it from different researchers, you get maybe a couple tenths of a kilogram per second of water vapor from a realistic water ice table. So that's not enough to explain these telescopic observations. But there are a couple places that you could potentially get a lot of water vapor. So I've kind of color coded here from resolved craters, poleward facing slopes, and unresolved craters. So craters that are so small that you can kind of tell it's a crater from the visible image, but that you actually can't resolve it in the visible and near infrared spectrometer data. And this happens a lot where the spectrometer footprints will be larger than the pixel size in a camera, which makes sense. You want to see what geologic feature is behind that spectra, and it's a lot harder to kind of pick it apart if you don't. have that high resolution image. And so these are models over the course of one Ceres year. So LSS, solar longitude of Ceres. For the Mars people, this is a different LSS, but measuring the same thing for Ceres. And one thing to note, let me just add the order of magnitude here, is that all of these order of magnitude kilograms per seconds of water vapor are really low. Occator Crater has 10 to the minus 2 because Occator Crater has a very large area, but a lot of these are in the 10 to the minus 8, 10 to the minus 6 kilograms per second of water vapor. So these small exposures are probably not causing all of Ceres' exosphere. But if you add them all together, you start getting a lot more, and then it's possible to have not huge numbers of craters. You don't get a crater bigger than about 70 meters. That's expected on Ceres over the course of Dawn's 3 or 4 year mission timeline. But we know craters that are on the tens of meter size are happening in like geologically recent time. So if you take, for example, some of these smaller spots and just keep adding additional, especially from the unresolved craters that are 10 to the minus 3, so getting up there with Occator Crater, what happens is you can eventually build up, I think the final number I came up with in the paper was close to 1 kilogram per second. And then the other thing you can do is model predicted impacts. And then if you add in predicted impacts, you get up to about 1 kilogram per second of water vapor. So the takeaway from this is that Ceres still has a very active water process. There is near surface water that's being exposed, and the result of that exosphere is probably, other than these huge telescopic detections that we're finding that still don't have great explanations, there's a large background amount of water that's being lost. So even if it's not staying liquid on the surface for any extended period of time, Ceres is currently in the process of an active, at least water solid to vapor cycle, not so much the liquid. And so the key takeaways from the water part of this story is that water ice really plays an active role in present day and geologically recent surface processes. It implies some sort of recharge mechanism too, because like I mentioned earlier, if you're constantly losing 6 kilograms per second of water vapor, you're expecting meters, tens of meters of subsidence at the surface. We don't see that. We also see variations in latitude that are potentially temperature dependent due to the in the hydrogen data. And so some exposure of additional buried water ice is probably possible, and probably something is going on, with the water cycle generally. And continued telescopic monitoring of Ceres is challenging, but may result in further confirmation that Ceres does have this exosphere, and then it's an active icy asteroid. And if we can put Ceres in that category, it comes in the same category potentially as other objects like Comet Pizarro here, which is a main belt comet. These are objects that have orbits like asteroids, but have dust tails that are inferred to be from sublimation like comets. And so understanding what this difference is between a comet, which is outer solar system, potentially venting off a lot of gas as it comes by on this highly eccentric orbit by the sun, versus an asteroid, which is much closer into the sun, tends to have more circular orbits generally, and tends to be rockier, where that kind of distinguishment point between those two is something that Ceres and other main belt comets kind of call into question. So again, how much do we understand water processes and small bodies in the inner solar system? We've learned a lot more from Dawn, but it opens up additional questions about where to place Ceres and amongst these other main belt comets and these other objects. Okay, and then switching gears over to carbon, which is the other thing I promised in the title. There are carbonates all over the surface of Ceres. This is some spectral data from the visible and near infrared spectrometer. I think this is band center here shown in color. The cooler colors are less carbonate and the warmer colors are more carbonate. Things that stick out again are Occator Crater, like I pointed out in that global GIF is here, if you can see my cursor. Halani Crater is another crater that didn't get as much attention as Occator because it doesn't have bright spots on its floor, but clearly exposed a whole bunch of carbonates in the ejected blanket. And Capallo is also in that same category. So not only are there all sorts of buried water ice features and evidence for that, there's also evidence of a lot of carbon and carbonates and other salts that are affecting Ceres' surface. Okay. So not only Ceres covered in carbonates, the bulk elemental abundances of iron and hydrogen suggest that there has been the addition of carbon and kind of dilution of water of Ceres' regolith from CI chondrites. So this is a plot from Prettyman et al. 2019. And so again, this is the kind of data you can get from neutrons, where it's not telling you what mineral the iron and the hydrogen are in, but it's telling you the relative abundance. So we have iron weight percent on the y-axis and hydrogen weight percent on the x-axis. Ci chondrites are shown in this star. We know the composition of Ci chondrites because we have meteorites on the surface of the Earth we can measure. And what these three different tracks, A, B, and C, are showing here is different amounts of additional water and different amounts of additional carbon. And the dots are data from dawn. And so it looks like in order to really match the data, you have to add some amount of carbon and some amount of essentially water dilution to be able to match the elemental abundances. And this is also borne out by trying to match the global visible infrared spectra of Ceres. Work by Simone Marchi and co-authors in 2019 found that in order to match the global spectra, the best fit included some amount of amorphous carbon. And that was an indication that the surface of Ceres might be a lot more carbon rich than previously thought from analog meteorites. Coming off the water part of the talk, carbonates also co-occur with water. So this is Occator Crater again, which is in the northern hemisphere, and it's that crater that's probably contributing the most water vapor in the present day to additional amounts, or yeah, in addition to the water ice table on for Ceres' exosphere. So it's one of everyone's favorite craters other than Occator. And so in this chart here, you're seeing the spectral intensity basically of water, sodium carbonate and hydrated sodium carbonate. And so water has this huge kind of area on the floor. This is what I modeled for the exosphere. But also there's signs of hydrated and dehydrated salts in this area too. And it appears then that if these water and these carbonates are co-occurring, maybe we're exposing them out of some global subsurface layer that might be a remnant of a global ocean. It's telling us something about the not mixed composition of Ceres' regolith, and maybe telling us something about the interior evolution of Ceres too. I know I limited the title, I limited the talk to the surface, but you have to get your surface material from somewhere. And then another thing about these carbonates and other high albedo deposits. So we're talking now about the bright spots that are not water ice. We're talking about the bright spots that are carbonates and other mineralogically fresh salts. So one thing that's interesting in this chart is from Stein et al. 2019, is that there are some of these bright spots that contain a lot of salts and carbonates. This is an Occator Crater that appear original to the crater. From geological arguments and principle of superposition and other things. There's other ones that appear to be eroding out of the walls of craters or in crater ejecta, which implies that they were already present. And the origin of these carbonates and potentially kind of concentration of them was not due to the impact or any sort of impact heating. And then again, everyone has to put Ahunamans in its own category because it's really not necessarily clear what's happening with this particular upwelling event, but something happened. And so again, we're seeing signs that not only are craters modifying the surface and potentially concentrating carbonates in these bright deposits, they're also just exposing extant carbonates below the surface. And then again, just to kind of just throw this in there, this is the phyllosilicate abundance map. So we're trying to understand where there are clays and other things that might be indications of water or other modification. The phyllosilicates and the carbonates don't necessarily always correlate. So showing here Occator Crater, there's plenty of carbonates, but it's not in a particularly phyllosilicate rich region. And one of the things we can start to do with all this mineralogical data is put together a concept of how the surface of regolith of Ceres evolved. But before that, we're going to take a zoom in at Occator Crater. Like I mentioned before, it's at about 20 degrees north, and it's about a 92 diameter crater, or kilometer crater. And what's really interesting is this bright spot at the center is a dome. So this is a flyover that was synthesized using the digital terrain model made of this crater. And there is this dome structure kind of inside this moat at the very center. And so this is one argument that this is some sort of resurgent dome type structure, and that it might be some of the freshest material in Ceres. Hydrohalite has been detected in this dome. In the paper that announced that detection, they make the argument that that implies that this dome is recent or currently upwelling. I think there's not a bad argument for it's very easy to lose water, create a kind of diffusive barrier to water loss from other material to kind of armor the outside. And then all it would take is small mass wasting events, since this is positive topography at the very center, or small impacts to erode that and periodically re-expose to hydrohalite. But again, the point of this talk is to not adjudicate controversies that might still exist in the dawn data, but to kind of present them as part of a larger story. So one way or another, there's material that's been relatively recently upwelled at the center of Occator Crater. The other thing that's really special about Occator is that not only do you have this hydrohalite in the dome and carbonates, you also have a pretty strong argument for the floor, where there are these lobate deposits that are very smooth on Occator Crater's floor, also having an enhancement in hydrogen relative to the background. So this is data that I helped interpret as part of my postdoc from Prettyman et al. 2021, where we took the geologic map that had been made by other researchers from the visible camera data, and then saw how it corresponded and correlated to different hydrogen distributions in the subsurface. And so what's really interesting is we do have this enhancement of water ice at the floor of Occator Crater. Unfortunately, the calculation that I did shows that even if you made this all pure water ice, you still wouldn't get up to 6 kilograms per second, but you could still be getting some additional water vapor from Ceres or Occator's crater floor. And one thing we argue in this paper is that complex craters might be enhancing water ice in the near surface as part of the whole melting and crater formation process. So that's something really interesting to think about, is that maybe the process that triggers this carbonate formation at the surface is related to the impact energy that's also related to concentrating water ice. So again, I think the carbon and the water story on Ceres is very difficult to pull apart if we really have these kind of cold hydrothermal systems occurring on the surface due to impacts. And the reason we argue that they're cold is, oh boy, is it hard to keep heat around on Ceres. The surface temperatures aren't particularly high. You're out at about 2.5 AU, so it's not particularly warm, but you could have fluids in the subsurface making a lot of different kind of changes to the regolith, freezing out and then being present there to be kind of remobilized by a subsequent impact. And then finally, again, just to show you, this is the sodium carbonate map. And so this is much better resolution than the previous one. And again, these bright spots on Ceres are just chock full of sodium carbonate. And so again, this is arguing for the carbon and water story being really intimately connected on Ceres. And I'm sure the astrobiologists in the audience are starting to have thoughts about this, and I will get to that in a little bit. And so this is kind of our current understanding or concept of how Ceres regolith has evolved. Something happened in kind of the interior of Ceres, whether or not this was a global ocean or an icy mud ball where the water and the lithic components were more well mixed. There's still a pretty strong argument, but it looks like the global ocean version is probably a little bit more likely. One way or another, you have this material that had both water as well as other major rock forming elements kind of sloshed together, and impacts over time have been modifying this aqueously altered crust. And then on top of that, you might have these post-impact hydrothermal systems that are further affecting the composition. And so this schematic on the right is from Simone's 2019 paper, kind of showing all the different ways you can have organics, carbons, ammoniated phyllosilicates, and other materials in the crust, and how what we're seeing at the surface of Ceres is this combination of both the original composition of Ceres, but then all these different modifications that have happened over time from all these different geological and astronomical processes. I mean, impact cratering, I'm not sure if it's fully geological or astronomical process, but it's a little bit of both sometimes. Okay, and like I mentioned earlier, there are potentially these cold hydrothermal systems, and to make an analogy to the Earth, this is potentially not dissimilar to how travertines form. So this travertine is really common around Albuquerque, New Mexico. And so when I was there doing my postdoc, we did a field trip out to a couple of different travertine sites. What's really interesting is that you can't see the sky in this photo, but this was in February in Albuquerque, so it was pretty chilly and snowy. But what's happening at this kind of vent site in an area that has undergone a little bit of heating, but not a lot, is a system where gas is bubbling out through the subsurface. Unfortunately, it's not a movie, but you can kind of infer that there's gas bubbles here. And these systems were not particularly warm. You can tell I walked right up to it. I didn't do the thing of like, oh, let's go right up to it and see if I fall in. But we got fairly close to these. The temperature of the water was ambient or just a little bit chilly because it was a cold day. And it was a place where kind of CO2 was bubbling up through the surface of this standing water and generating kind of the precursors of travertine deposits. And that's not to say liquid water is stable anywhere on the surface of Ceres, but it's this kind of idea where maybe you have this water and this CO2 gas that are interacting. And what ends up happening is eventually the water kind of goes away and you end up with these, in this case, calcium carbonate deposits that are really beautiful. This was actually at a travertine mine outside of Albuquerque. So this is where people were getting their kitchen tops from. But you can see all these different layering processes, all this different folding, as well as kind of veins that are vertical to the present flat. And so this is suggesting one potential Earth analog for these sodium carbonate deposits on Ceres, where maybe as the original crater heat was lost, and you have CO2 dissolved gas, maybe in the original ice that's now released from the impact, you can start to have these deposits that will freeze and be more permanent and in the rock record, but then you also have some record of the gas that's lost. And so we've talked about water vapor, we've talked about CO2 being lost. This is also a taste of some work that I'm currently conducting with colleagues at Planetary Science Institute and Jet Propulsion Laboratory. So stay tuned to a future future LPSC for the actual or future conference for the actual results. But one question we thought, especially seeing the role that CO2 gas played in some of these carbonate deposit formations, is could we actually trap a record of CO2 and water loss somewhere on Ceres? And you could not get away with me not showing a permanently shadowed region plot. I do too much polar science. But this is a quick schematic showing different planets and their different obliquity and whether or not they have these permanently or persistently shadowed regions. Mercury has an obliquity of 0.03, so you better believe that there's topography at the poles. It's possible to capture volatiles in them because the temperature is going to be drastically different. And again, this seminar is not about Mercury, but one thing that's really interesting about it is Arecibo was able to detect these kind of radar anomalously smooth regions at Mercury's poles, and they were later confirmed by Messenger and other work to be volatile deposits on Mercury. So even in one of the hottest places in the solar system in terms of planets in our solar system, you can still have volatile deposits at the poles. Venus, we don't know, it has a low obliquity, but those clouds are not great. The Earth has enough of a tilt that there's permanently shadowed, not permanently shadowed regions, as well as Mars, but the Moon and Ceres have these relatively low obliquities that allow for, basically, if you have an impact crater at the pole or any sort of topographic relief, you can create these areas that never receive direct sunlight, even if they receive re-radiated energy from their surroundings. So on the Moon, these are places where you can get down to 50 Kelvin-ish, 55 Kelvin temperatures, as measured from the Diviner Lunar Radiometer. And so those are Pluto-like temperatures in the inner solar system. So for Ceres, the obliquity is 4.02. This has potentially changed drastically in the past. So that's why we're calling them persistently shadowed regions. But these are places that could capture volatiles that have been released from the mid-latitude or equatorial regions. So could these PSRs on Ceres trap gases that had been released from Ceres' interior, either water or CO2? And the answer is probably. This is a illumination map made from different image data from dawn. And brighter areas are more illumination, darker areas are less illumination. And so there's some areas that really don't receive any direct sunlight. What you can do though is stretch the crap out of your images and use scattered light. This is something that with a little bit more refinement, the ShadowCam instrument on the Korean Pathfinder Lunar Orbiter is going to be doing for the Moon, but for Ceres, the framing camera was used. And so there are higher albedo deposits inside some of these craters. And hopefully if we've taken anything away from this talk, it's that high albedo things on Ceres could be salts or water ice, we don't know. But visible and near-infrared spectra were taken of these craters to confirm that there was water ice with a little bit of ammonia in there. And that ammonia is interesting for something we're going to revisit in a second. So the permanently shadowed regions could capture a record of the water and CO2 release, as long as those PSRs are stable enough through enough series of obliquity changes. And so that's some current work I'm doing right now, is trying to understand the volatiles delivered to these PSRs from different sources, and to really understand if we could have records of volatiles delivered to the poles over geologic time like we do on the moon, but on Ceres. Okay, so to recap our questions about carbon and water, how did it get there on Ceres? What's the carbon and water's long-term stability on the surface, and what does this mean for small bodies evolution? Small bodies evolution part is tricky. So like I mentioned and alluded to earlier, there's also ammoniated species on the surface of Ceres. The temperature required to generate these is not warm, and it implies temperatures that are potentially colder than are currently in the asteroid belt. And a lot of these migration models that are motivated by understanding kind of the NEAS model, solar system development, and kind of the Grand TAC model and everything else for moving your small bodies around, suggests that there are multiple pathways for a Ceres-like object that might have formed around Saturn's orbit to be injected into the asteroid belt. This D'Souza et al. 2022 is one of the many models, and it seems like it's dynamically permitted to have a Ceres-like object be implanted into the main asteroid belt. And it's almost even required or very strongly applied, at least from the surface geochemistry, that some of this aqueous alteration needed to occur at temperatures that are much less than what we'd expect from current temperatures on Ceres or temperatures in the past. So this means that our entire model of the snow line might not really make a difference, because if you can throw your icy dirt balls from the orbit of Saturn into the asteroid belt, that's a whole different level of mixing. That also supports an idea that maybe redelivery of water and carbon to the Earth in the Earth-Moon system and even to Mars is not as unlikely as potentially previously thought. And so this is something that is, I think, really been the major change from our cartoon model that I showed at the very beginning of understanding solar system evolution. It seems like small bodies really do carry essential elements and mix them around the solar system. So I know this is also an astrobiology seminar, so I wanted to direct you all to this this chart from Castillo-Rojas et al. 2021. That's basically arguing that we have water, energy, and carbon and nitrogen and other important, relevant to biology elements all happening on the surface of Ceres. And so now being able to tease out what the history of that has been in more detail, and to understand kind of what conditions existed on Ceres' surface in the past, is really critical for understanding, I guess, generally the habitability of Ceres, but also to understanding the role that these large icy asteroids have in kind of either synthesizing these compounds or delivering them to the inner solar system, or just how typical these kind of combinations of chemistry and temperature there are in the solar system. So we can't talk about space exploration without talking about future potential missions. This was one of the ones that was studied as part of the Planetary Science Decadal Survey, again from Julie Castillo-Rojas and team. And they're arguing for a Ceres hopper that would land at Occator Crater and hop and take in situ measurements of different carbonates at different places to really understand the geologic history. So to recap our questions again, we have some answers. How did water and carbon get there? Likely from Ceres, it's due to re-exposure from a primordial ocean or some sort of primordial factor of the interior. And why there's so much carbon and water ice there is because Ceres likely formed in about maybe the Saturn orbit is the current thinking, and was re-delivered into the asteroid belt. So snowline in this case is not a helpful conceptual model to think about this, because we know about these reservoirs being mixed. What's the long-term stability of water ice and carbon on the surface? Water ice in total from both a buried ice table and surface exposures get you up to a rate about 1 kilogram per second. And carbon is kind of mixed into the surface regolith. Hopefully that argument's been made from the elemental abundances as well as conceptual models of how carbon could be concentrated when a complex impact crater forms, and then remixed and re-exposed as subsequent cratering occurs. And what does this mean for small bodies evolution? I think this is something we're still trying to really tackle and understand. Again, Ceres is kind of an outlier for being such a large object, but it's showing that all these active processes, both in terms of outside activity from impact craters, as well as endogenic activity, like in the example of the Hunamons or the example of the bright spots at Occator Crater, are really still modifying and changing the surface. And so small icy objects in our solar system seem to be these great laboratories for understanding how water and carbon have been interacting, how they've been delivered different places, And I think there's still a lot to learn, as evidenced by the fact that there's a Ceres lander concept that was studied as part of the last decadal survey for a New Frontiers level competed mission. I think those are all of my slides. Thanks so much for your attention. I'll go ahead and kind of leave our answers, and I, in true science talk fashion, answered 2/3 of the questions. And that last 1/3 one is a really gnarly one that I think we're going to have to continue to look at in the future, both at Ceres and at potentially other icy asteroids, and to really start to synthesize what this means and implies for the chemistry of the solar system. So thanks so much.